So today we go to the hairy part. The other day we had a very nice overview of SLAM where you just need to focus on the cost function and the vector graph. And so today we go to meet the devil. The devil is in the details. Each factor we're going to expand it and see what's going to happen. So yeah, so just to capture, so generate the cost, we're here in the cost. And we need some mathematical tools to proceed with handling these sensors. Hopefully we can get to the Lidar part, because I think we can cover maybe 20 slides today. If you have any question, raise your hand so that I don't need to break my keyboard. Raise your hand for the question. Also, you have a job. We did a survey, and then this is your interest in the sensors. And yeah, the IMU is the best, it has the most interest. And then the second one is the LiDAR, then the camera, and the GPS. So these three are I'm familiar with. This one, they have a new paper about G-Wings as well. I can give you that reference. Hopefully we can cover these three. We can go to the camera to get 29 by now. If not, session 7. So first of all, I'm pointing out like, okay, our star LiDAR will sense RGB camera, Z stereo camera, alpha sense 5 camera setup, live watch, and then this is INS systems from the vector. What do you think these have in common? The live watch is the LiDAR, but in this view. Yes, they all have unused. Level has unused. On the setup down, but this one has. Why do they put the unused into their sensors now? Because first of all, it's cheap. It doesn't cost a lot, and second of all, it's very convenient for you to do calibration. At least that's from my experience. So IMU is actually a very powerful sensor, and you see the German what do we call them in the army? They put this sensor into their rocket and they wreaked havoc on UK for the whole World War II. And that's at that time it's it's this big, but it's doing its job. Now you can bought one for a few dollars from a hobby shop to do your Arduino project and probably learn something. But for like a navigation system, they use a one with shielding and then maybe GPS. So that's why I find GMU very powerful. Of course, it's very complicated because you need to know about the dynamical, mathematical derivative, manifold, mathematics, everything just to get to use it. But when you get to use it, you are kind of addicted to it. Put it in every of your sensor fusion pipeline. Okay, so before we go to the things, the main content, we can try to agree on the notation first because it's more it's more informative to look at an equation and look at its notation to decode what information is there. So in most cases, people try to estimate orientation, position, velocity, and IMU biases. What do you think we need to estimate the velocity and biases? Because the IMU is there, so you need these states to model your dynamical system. If you don't have IMU, you probably can throw away these states. Yeah, less states actually less problematic. Then yeah, so these are clear. So when in this slide, right, I'm going to use the hat notation to indicate an estimate quantity. Yeah, we start from a true state, but if you put a hash there, you know that okay, there's a true physical quantity out there, and I'm going to use a brief to indicate that it's something that we are using, we are propagating, or we are measuring, right? So it has something to do with the sensor. And then this is a constant multiplier. So we throw some numbers into our model, and then we just accept them as fact. And then we just use this notation. And so I'm going to put the frame of reference on the superscript on the right hand side, on the left hand side, like this. Sometimes I throw away the frame and then I just put the time. Okay. So this is not, yeah.
So could you give the example of the bias? Like what is the bias in the
Bias probably if we don't finish today, we have to go to the next session to go to it. But the bias is actually quite simple. It's just a measurement you read it. You have the bias, you have to throw it away. You have to somehow estimate it to cancel it out. Yeah. It's like an offset. We will introduce it in the MU.
It's like a correction. You add something to the value already.
Yeah. So before we handle a sensor, I argue for, in my paper, I argue for 4-step process here. So the 4-step process is first, you need to state explicitly as clearly as possible what is the relationship between your measurement, your states, your prior information, and the noise, as explicitly as possible. If you cannot do it, then you're going to suffer later on. The covariance is like, we need to know, okay, how is this sensor, how noisy this sensor is, how noisy this measurement is, so that we can appropriately put a weightage into our cost function. So in the literature, people usually just start from the number 3 and number 4. You just say, okay, this is the residual, and they're just going to show you what is this minus operation calculating. Yeah. But it's actually starting from the model where you have the model, then you throw away the noise, you put in your estimate, and then you subtract it from the measurement. That's what the residual is trying to do. And then the Jacobian is like the gradient. You have a factor. You are trying to estimate from the residual how different this is from your measurement. And the point is to calculate the gradient to go to the right estimate. So the Jacobian is another bread and butter of our process. And this one applies for both filter-based common filter and optimization. So what is the difference between the filter-based and the optimization?
Correct the pass the optimization is.
No. No. In technical details, in filter, you just get the measurement update once, right? Common filter. You get the measurement, you calculate the common, and update your state. Optimization is you get the measurement, you calculate the residual, update your state, linearize it, calculate Jacobian again, update again. So up to many times you set into the solver. And this is very important. So this I put it first here. So I think you know what this one is?
I can read it, but
I think I look it up. It's like a 4 noble truths in Buddhism. So whatever you do, just keep in mind these 4, hammer it in your head. The model, the noise, the residual, and the Jacobian. Keep it in your mind. This is just raw. It doesn't hurt.
looks like.
Do you have any questions, Jenna?
No.
Okay. So we just start from a basic example. My PhD in first year, you have an anchor set up in the environment. The anchor position are measured using motion capture, and you have you measure the distance to the beacon, right? So we just apply the formula proof there. What is the model? The model is basically just the Euclidean distance from the robot pose. The Euclidean distance from the robot pose to the anchor, right? Corrupted by noise, right? So this is a scalar observation. So the noise is basically just a scalar, so it's easy. When you write the optimization, you just put a fixed number there. tool you can think works. The residual. So this model, we plug our estimate in, right? And then we get the residual. So basically, how much our estimate is deviating from the measurement. It's going to tell you how to correct yourself. And then you calculate the Jacobian. Is this straightforward? Yeah. It's just a V, norm of V, partial differential over V is basically V normalized. Yeah. Okay. Accepted as true. No question? Okay. Now, this is slam, but like where's the slam box here? How is this slam?
It's localization.
That was the map.
This thing.
So it can be a map when you don't know this one.
Yeah.
And you try to make it into a state, right? So instead of the model being like this, you just put it in an estimate here, right? And then instead of just Jacobian of one stage, you can do Jacobian of another stage. Right? It is the same as this one, but this with the minus. Right? So this is localization and mapping. The map is actually the anchor position. Mhm.
How do you estimate the covariance?
How do I estimate the covariance? Because we know that, okay, the measurement is going to be corrupted by noise, right? And the noise is, we're just going to say it's going to be Gaussian, and the variance is empirically, for example, the sensor I try, 5 cm, another sensor can be 10 cm.
You just set a value of sigma based on your experience.
You also kind of can collect the data and then chart it out and then see the distribution. Yeah.
So that's,
That's what I did.
That's what they mean when they say modeling the sensor noise.
Yes.
This sector value.
Yeah. This is a simple sensor, so you can kind of do it.
But could you do this probabilistically and not do squiggle the rounding variable instead?
That's for the bias, I think. Yeah, you can. I mean, if you can put another like dynamic process here.
Yeah, but because I was going to say probably the noise is actually depends on the distance to the anchor is.
No.
No?
Very minor.
It could,
Yeah. It could, but it's very minor because, for example, some sensors we use the kind of two-way time of flight.
yeah.
Okay. So if I shift the anchor from the body center, like for X here, why do I do this? Why do I do that?
That's right back there.
Yeah, but like, why do I do it? Why do I put the anchor away from the body center? What do I gain from it?
Oh,
What I gain from it is I get to couple my observation with the orientation. So instead of just estimating the position, now I can also estimate the orientation. So same procedure. But now you don't know the orientation. You have to estimate the orientation. And then what the heck is Jacobian of the rotation? Like I said, Jacobian is the gradient, right? So you're trying to know, okay, which direction I should update my rotation matrix, right? But you don't, so if it's a vector, you just plus something, but that's a rotation matrix. So if you want to update the rotation matrix, you have to plus it, but in its own kingdom, which is the Lie group. Understand? So that's why we have to talk about, yeah. So localization, sensor fusion, we always have to involve orientation. Even if you have a camera, you always have to worry about the rotation between the two cameras. And we represent rotation by the rotation matrix, and the rotation matrix are special objects in the Lie group, special orthogonal XO3. And all of the calculation on vector, we can actually mirror it in the Lie domain. But we also have to learn how to do it. So just quick question, do the vectors that we are working on also belong to some Lie groups?
What is the group?
Lie group is like the thing that the rotated matrices belong to. The group of the mechanical objects, the group of mathematical objects that the rotation matrix belongs to.
So just the matrices, like linear algebra, that's what you mean, or I don't know.
You will see soon on the next scary slides. I think position belongs to SE3, right? Lie group.
Position belongs to R3, Euclidean space 3.
Okay, I'm thinking of.
But Euclidean
Basically
space is
body
also
rotation,
in
yeah.
groups.
So what is the Lie in here? What is, because like yeah, SO3 group, it's pretty straightforward, but like why there is a Lie?
It's the name of the guy.
Yeah, but is
So
it
you
some-
have
it's a,
you
is it a
have you have a
different
vector
just-
space now, right?
Yeah,
On a vector space, you can do plus, you
Yeah.
can do minus, you
Yeah.
can do inverse.
Yeah.
But rotation matrix,
Yeah.
you can't just straightforwardly plus two rotation matrix together. To plus two rotation matrix together, you need to do a special operation.
yeah.
So Lie group means they are trying to make the normal vector space something more abstract and more general. Okay?
It's like the group of possible rotation
Okay.
matrices. Yeah, it's very abstract.
Yeah, you can actually read.
I never.
So if I want to
really
think
heard
about
of
it, if I
much.
convert this rotation matrix to the Lie space, I can do plus minus inverse.
Yes, yeah, you can understand it that way.
Yeah,
You can't plus minus rotation matrices. But now if you have this Lie theory, you can actually abstractify the normal plus and minus operations.
So we had a question there yesterday. Can you take arbitrarily large rotations in the Lie algebra and just sum them? Or is it only
What do you mean
infinitesimals?
arbitrarily large?
Like you have, say you have some rotation matrix and you take it to the log of it.
So
Take the log of it,
Uh-huh.
and then you have some other enormous rotation. You take the log of it.
Mhm.
Can you add this in this?
Exactly, the log operation is actually the minus operation.
Right, and that, and my point is, what we were wondering is it not true only in a vicinity of one of the rotations?
That's the language they try to talk about when they want to fix an engineering problem at hand.
Yeah.
Right? So they say, okay, local facility, blah, 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 something like that. But I'm trying to make a complete picture. This is actually not complete, but I'm just trying to
Right.
make it into slides so that it's like a handbook. You can actually work on assignment 2, for example, like that. So, okay, Lie group. And Lie group has there are many Lie groups, but we're just focusing on the SO3, which is the group of rotational matrices. Yes. It's only complicated when there's a rotation in the problem. So we just define the group of as a group of rotations here. So in this Lie group, we also often have to worry about the skew symmetric matrix. Means basically the skew symmetric matrix is matrix representation of the cross product in the vector. So you have vector A and you have vector B, right? U, A, B, A cross B, you get another vector C. Right? So you can do it in a geometry way, or you can do it in a matrix way. Yeah. And if you minus C equal to B cross A. If you cross from A to B, you get this C, but if you cross from B to A, you get this C. Right? So that's what this is trying to tell you. And we need to keep track of this to solve another problem in the next slide. Rodrick's formula is basically converting the rotation angle in R3 to a rotation matrix in SO3. And we use this one to define our exponential function. Right? We use this formula to define our exponential function. And we also have an inverse function to get from SO3 back to the rotational vector. Rotational matrix, rotational vector. We have the log function being the inverse. And then now we use these to represent the plus and the minus operations. Right? So now with these tools, we can start doing the Jacobian on the relation matrix. Okay? Are you confident you got the gist of it? Only 2 slides, right?
I have a question.
Yeah, we have another slide.
What was the answer to the question, do position and velocity belong to lie group?
They also belong to the groups. Yeah, but the box, the plus and the minus of those Euclidean space is the same as that's what we are familiar with. It's just that when you go to Lie group, you have to generalize the plus and the minus operations. So so these are like some engineering tricks to remember. So when you calculate Jacobian, you usually do this kind of approximation. Right? Exponential function, it's basically like Taylor expansion of this function into this form. You can think about it that way. So most of the time you do Jacobian, you just do this. I guarantee. And then now you can see the Jacobian, right? If I provide this one, I just use the plus and then use the minus. It's something that you are familiar with already, right? It's a function, and then you try to find the derivative there. You just use the plus, minus, and the limit. But now, because we generalize our mathematical operators, we now can do it for the limit. And pay attention to this: the function, the domain, and the functions. So if we have this function, right? If we have this function, this is the function. This is the m, and SO3 being the n, right? The n. Then if you apply this Jacobian formula, people calculate you this formula for the right Jacobian of rotation matrix. And so now you see, if you calculate the Jacobian, and then you can find a small enough vector to update your rotation matrix. You use the Jacobian here to update your states. So this is actually equal to R box plus Jacobian right of. Yeah. So this is what you do. You calculate the Jacobian of whatever, and then you try to calculate the gradients, and then you update in that direction. So don't think too much about the technical details here, but what we're trying to do is we're trying to generalize from vector space to Lie group to do the gradient update. Okay. You don't need to know, but because I need to know, because later I'm going to do a dance with this one. Most importantly, you need to remember the chain rule. We have a compound function, and we can do Jacobian of the first layer, then another layer, and then another layer. Right? Suppose in the assignment 2, you probably will have very like compounded, very highly compounded function observation. So we just use the chain rule. Okay. I mean, if I don't have to make a living, I just study this all the time. Okay. Once yet, I told you like
No, I definitely.
anybody else born on October? Go. You probably need to remember this. Lifting function, right? Right. Equal to R I plus. Right. You need to use this one. That's all. Go. Come here. No. Is it that hard? Okay.
So what's the problem? What are we supposed to do?
You calculating that Jacobian?
What should we say?
Calculating this Jacobian. I put it like it was many slides before. But now I want to save it now. You think you can do it? What you are right of R hat I plus x, right? I'm just approximating this with this one. Plus constant, subtract constant, right?
Which means it's right, the B half,
This is degree. So it's a measurement.
sorry.
Measurement is a fixed number.
Yeah.
So the way. So I only need to care about. So I can throw this away. I can only need to focus on this vector inside this norm function. And
Take the normal X.
R hat x plus R hat x plus C1, right? Okay, this is constant. We are not doing, we are doing partial differentiation on this variable, so we can throw away this one. I mean, we can put this one into this one, and then this one I also told highlighted. That's
You put the x,
Yeah.
start to multiply x with the constant.
differentiate with not with respect to x. So this is now differentiated with respect to phi. At the phi. So now I swap the place of this guy with this guy using this formula. Using that formula. X. Right. So what we have here is R hat x and 1 right, plus some constant, right?
Why did you split X and C delta phi?
R has x delta phi plus c minus c, right? So okay, so now it's the, so this is a constant matrix M multiplied with the vector y plus x minus x, right? So now you can actually do a simple, what is it now? It's going to be R hat x using exponent plus c minus c.
It's just equal to the cross.
Y is a function of the square root. Y is, I'm just simplifying the notation. I put the delta phi as y now. I put the R hat x as an M now. Denominator negative. This is negative? No, it's like in the.
I mean, it doesn't matter.
This is
You're
negative,
there's a
right?
negative inside the magnitude sign, but it goes away in that case. I mean,
In the.
below the line, there's a bar minus.
You mean this one? Which one? This one?
This one.
This is minus. What? Because I flipped these two.
Yeah, that's what I'm asking. Why did you flip it?
Because I flip it so that I can get it to this side. So that it can be a matrix times a vector that I'm taking the derivative on. If it's like a vector that is like in this excuse the matrix form, what is the partial differentiation of a vector matrix anyway? We're not dealing with a tensor here.
And so what we did was to use the chain rule to put so you get something like 1 over Rx plus P half minus PA, and then you take the derivative of that. In that function is that.
But we're doing it on the rotation matrix.
Oh, we also did.
So did you get? Did you
It
arrive?
doesn't look the same way, but it's very similar.
Uh-huh.
We use constant folding. Okay.
Like we didn't do all this. So that's why I highlighted the two. Yes, so you have, because I'm doing this, I'm doing basically this, right?
No, that we did. I mean, we didn't rename everything. So I'm not so sure if it's what to say. Like we didn't use like C1, C2, Y.
So what we learn is basically rotation matrix multiply a skew symmetric matrix. This one is in the literature it's called action of the rotation group. So just to learn, I mean, I guess you can go about just fine with these two tricks. Okay.
Can you describe the denominator, function, like where, how did you get to my and then this?
Maybe I confuse you because what we yeah, just ignore it. Right. So now we are here. This is a matrix, right? This is a big 3x3 matrix. This is a vector. This is a constant. We are doing the norm, so we just do the derivative on this. Yeah. Okay. Clear, right? So assignment 2 should be easy, right?
And at the bottom there was D R cap.
Uh-huh.
So and that we can ignore.
You see this, nothing here. We have to do this. Because by Jacobian, if you add something to the relation matrix, right? Then you do the Jacobian on that small variation. So that's why we do it exactly like the book, right?
Okay, so that is D of D5.
Because this one is the approximation. Yeah.
This section.
I mean, if you read the paper, half of the paper is the call function of the factor graph, right? The other half in the appendix is basically this. That's how you fill up the pages. Okay, we go to the LiDAR sensor. And I don't know why, but I feel like the LiDAR sensor is the least problematic sensor to handle. Do you agree? You just have a bunch of, you just have like some cache by it, then hook it up and then get the data. So the LiDAR, there's no magic. There basically we started out as a one line light laser measurement, right? And then they spin it around. They have a 2D LiDAR. Now they spin it around. Then vertically they have a 3D LiDAR. That's all. So what you get is just a bunch of distance measurements from the body frame. Any question on this explanation?
Are you distilling it here? Isn't that the issue?
Yes, motion distortion. Yes, you have to, because there's a rotational, there's a spinning mechanism inside. So what you get is not at the same time. The point cloud is a sequence of points, not like an image. When you get an image, you get the pixels at almost the same time, right? The value of the pixels are almost at the same time. But when you get a LiDAR, the points in the point cloud are at different times. So this is a big issue if your vehicle is moving very fast, right? So this is just basically cylindrical coordinate system in a splitting LiDAR. You get the points in this one. But now, so okay. So in the traditional method, for example, in image, you're going to extract some corner or some shapes or some surf features, right? In the LiDAR, it's usually, I mean, the first paper came out by Zhang Ji. It's actually quite simple, where they just calculate the smoothness and strength. The smoothness value on a scan. If suddenly there's a jump in that smoothness and strength, basically, if you look at it, this is basically just calculating the jump in the derivative of that line and that single line. If there's a big jump, then it's a corner feature. But if it's low, it's a surface feature. So they just do the feature tracking like that. And then people also propose circle, which is basically fitting ellipse into that voxel of the points. So And then so people can match the circles of different orientation and ellipsoidal parameters together. So this paper from UBON, they do it at different resolutions here, and that's how you do feature association. Previously, just like surface to surface features on edge to edge features. Now we do surface to surface features at different parameters. And are you familiar with this one? So they say, no, I don't want to do feature anymore. It's just like too complicated. So they just like whatever point you have here, right? And then this is your point, right? Just find the 6 closest points and calculate the normal in the beginning. And it turns out the simpler the better. It turns out that this simple feature extraction association is quite elegant and effective.
But you need to know the location quite well, right? You can't have a large search space. Otherwise, it will get pretty expensive, right?
It's actually not that expensive.
Um,
It's not expensive, right?
Sure, but let's say that you have lost track for some time.
It happens to
And
all
the
slide
search
method.
space become bigger. Maybe it's a different problem. Maybe it's a different problem.
So let's just you turn it on. You have the first line, you just put into the map directly. The next scan, you just do k nearest neighbor association, and then you just build the odometry on top of it. Yeah, it turns out it's actually the best in the literature. I actually, when I did my slick paper, I was trying to beat this puzzle a lot because it's very efficient and it's actually very accurate.
I have a unrelated question. If we go to the first slide of the Lidar, what is the encoder?
And the encoder counts the so like the outside you have 1,200, sorry, 1,024 vertical channels. The encoder is to tell you that, to tell you which vertical channel it is. Yeah. Okay. So that's the front end of a Lidar SLAM. Now we go to a more fundamental issue. Like we said, right? A scan is like 0.1 second long from TK to TK minus plus 1. Let's just assume so. And it's basically just a bunch of points that are in this frame of reference, right? In a body frame at that particular time. Let's just say your Lidar is moving in this trajectory. This is in 1 second, right? So it's the sweep, for example, at this point, you measure this point. It's going to be in the body frame at time t1. And then here, you measure another point. It's the point in time t2, right? But they package all of the points together and send you at time tk plus 1. They package all of the points in this period and they send you at this time. And then when you do SLAM, your estimate is only up to tk plus 1, right? The beginning of the scan. So you don't actually have the information of the pose in this period. Then you have to use what RMU to propagate the pose from this point to the individual position. So you can get, like, for example, in that 0.1 second, you have 40 samples of RMU. You can propagate the pose to get you 40 poses, right? In this sequence. So for this point at time t1 or ti for the point in the point, we try to find the 2 propagated poses that are closest to it, right? And we're going to do the linear interpolation to find the pose at the exact time ti, right? Pose at the ti is the linear interpolation of the 2 RMU propagated points, right? Linear interpolation because we just calculate the time period here and then put it into that interpolation formula. Very simple, right? And then when you get a point at the body frame, you can calculate the point at the work frame. Spherical linear interpolation. It's a function for quaternion. Yeah. In CPP, in eigen, they just cause log. So to calculate, this is exactly the formulation. I put it in the comment in the assignment. So you can calculate the point in the work frame and the point in the body frame at the beginning of the scan. Okay. Question. What is the point that the work frame used for? And what is this one used for? And what is this one used for? Just tell me what is this one used for? The work frame. Which frame is the map in? So what are you going to use this one? Yeah. You when you finish localization and you want to put marginalize that point cloud to the map, then you throw it in like that. You just throw this one in. But you want to do association, you want to do direct map, for example, direct map, this is the map in the work frame. The points here are in the work frame, right? And then you have a point here. It's in the body frame, so you have to convert it to the work frame to find the nearest neighbor here to do association. So the answer for this one is association. To match the scan with the map. Because the map is in the work frame, so therefore it also has to be in the work frame to do the association. But for the body frame, what is the use of the formula in the body frame? Is the frame tracking for the building of the cost function. So we go to the next line, which is what? So the four noble truth, right? The first one is the model. Assuming that you have a plane with the normal and the mean, right? And your point belongs to this plane, then basically we just use the plane formula, the plane, the parametric model of the plane, put the point in, and then it should be 0. Basically the distance of this point to the plane is 0, right? But I said it has to be as explicitly as possible. So I just put, okay, this is the noisy point. If I know the noise somehow and I remove it, then I get the FB. Okay, then I get the true point, right? And then I transform it to the word frame, right? This is at K. So if I have the point here, in the body frame at time tk, and I know the pose here at time tk, and I transform this whole thing into the word frame. So this whole thing is in the word frame, right? The normal vector is in the word frame. The normal vector is in the word frame, and the mean is also in the word frame. I'm sorry, I should minus this one, I think. This one.
So you mean that the point comes, you assume that the point comes from a local plane of some kind?
Yes.
Okay, I see.
I mean, the point has to belong to some plane.
Right. But if it's on a sphere, you just say it's planar if you go close enough.
Actually, in the sphere, you can actually assume that, okay, maybe in this like 10-point neighborhood is actually a plane. For example, when I did the Lidar or geometry on the aircraft, right? The aircraft is cylindrical, but it works just fine with the nearest neighbors.
Okay.
So what our model? Our model is that this point belongs to a plane. That's all. Covariance, of course, the point is noisy. The thing is, this one, when you calculate it, it's going to be a scalar. So let's just assume that the weighted is going to be a scalar again. Right?
Can you explain why is it 0 again? I understood
It's
R
the
K.
equation.
So
You
you
have
take
a- you have
the
a-
dot product.
You have a point, right? A point belongs to the plane. P minus mu n should be 0.
You're basically saying the projection of the point onto the plane should have 0.
It should be in the plane.
Yes.
The geometry, if you have a plane and the block point belongs to the plane, then you just describe it by this equation.
So how do you get the surface normal?
Ah, good question.
Good technique. Ask him the question.
You estimate it by like
Yes.
aggregating points locally.
Yeah, that's what I mean. If you have a map, you just like do the gain and search. For example, I'm talking about the direct method. Right? If you have a map, you just do the nearest neighbor and calculate the normal and the mean. Uh-huh. So where is it from? It's from the map. So if the map is critical, you can't do slam without the map, but it's not that problem.
So then you assume map is correct at that point.
Yeah, because we already marginalized it, so we just trust it. Oh, Jacobian. Can you come up with this one? This one is simple, right? Yeah. I like Jacobian. It's like it's very meditating to calculate Jacobian.
Start with the lift. Always a good trick.
So this one I can put it. This one should be the constant. It's fine. I was it's supposed to be the constant. It's fine. I can put it inside, or I can put it outside as a constant.
Oh, but you put the.
So because it's a constant, so we can ignore it anyway. So let's just write it like n transpose r f plus p plus constant whatever, right? And then we calculate Jacobian based on this position and this is the orientation. Right? Then we can actually ignore everything and then just keep this one here. Right? Agree?
Why?
So,
Why?
Because it,
And what happened to Ni? Like why
only
there is
one
not
term
F?
depends on.
okay. So n pose r hat f plus n transpose p hat plus c.
Okay.
Right?
So just before, what happened to Ni? Why there is no F minus Ni?
Mu is constant.
Okay, it's constant.
What did I say about the third point in the noble truth? Right? Throw away your noise, plug your estimate into.
Okay, so this is noise.
This is the residual part, so we throw away the noise and then we plug in our estimate. What we need to. So this is our model, right? This is
Yeah.
this is true states, right?
Yeah,
And this is the noise, right?
yeah. That's,
So
there
the-
is this measurement. Ah, okay. So the measurement minus noise. Okay.
So in the noble truth number 3, throw away the noise, plug in your estimates, and then start doing the residual and Jacobian on it. In the paper, they usually just start from these two. Then you just where the hell are these assumptions from? In the literature, they also just throw away these, so you also don't know this is whether this is true state or the estimate.
Yeah, that's true. They are hard to do.
So you do in Jacobian. So this thing, this one I'm rewriting this thing here, like this, right? You just put the brackets away, you get the normal into it, right?
Yeah.
And then we are trying to do Jacobian on the position, right? So this one doesn't have any Jacobian, and this one doesn't have any p in it. This one also doesn't have any p in it, so we only have this one. So we take the Jacobian of this one, you only have the and left. Okay? Now this one,
Now you lift.
yeah, now I lift. Hold on. Come on, this is very meditating.
I don't like to screw up.
So, what do? We put n r hat plus a small variation f plus p in, right?
Yeah.
Lifting function. Then this one approximated with n r I plus delta p. Right? F plus p and right. Now just ignore everything that doesn't have anything to do with this.
Should be n parentheses before the f, right?
This one, yes. And throw away anything that doesn't have anything to do with this, so I can simplify it to n plus r hat f plus some constant, right? Right? Then you do the Jacobian over this one, right? And then you do the trick where you swap the two places again. Then it's going to be Jacobian of n transpose r hat f, right? Minus, because we swap the place, so there's a minus here. Then we arrive at here. This holding is here. Yeah, you have to practice yourself. So that's why in assignment 2, I didn't ask you to go calculate directly. I'm telling you to go look into Jin Tong's code and try to rewrite it into mathematical language. He did the same thing, but it's on. He did it on the quaternion, so
I think the right side of the equation should not have partial.
the right. This
That
one
is the partial that you have. Like it says you should take the partial with respect to.
With respect to this.
Right.
So if now, because you said that now we do the motion compensation, so we put the point back to the initial pose, right? But now it's not. If I'm, well, I mean, I did do that method quite a while, and I realized it's not that necessary to do that kind of formulation. I just deal with the point measured at the that time exactly. So it looks simple enough, but yeah, it's actually you have to use a chain rule. So you'll probably have to go into my code to see how I do it. Doing it is going to take forever. But the point is you're going to need to use chain rule and the formula on the Jacobians. Okay.
But so do you solve this if you like if you sit down to build a stamp system? Do you solve these equations for your particular setup, or do you actually use like a symbolic?
I do it myself. I do the maths. Yeah, I do the maths. Like you said, you can just do the first order approximation and freeball it, which is okay.
Yeah, I was wondering, like, let's say you parameterize the rotation as a quaternion,
Yes.
because it's a bit simpler to renormalize that,
Uh-huh.
and then you just optimize in Euclidean space. How big of a difference do you think that would make in the end? Let's say you optimize a pose, for example.
I don't know. I never did.
Yeah.
I never did that kind of thing in the Euclidean space. But because you see, actually in the quaternion, right? This quaternion operation. So in rotation, 1, 2, they divide as a log function,
Right.
right? In quaternion, they divide as 2 vector of this quaternion 1, 2. Right? This one is an approximation. Just the vector part of this quaternion. So this is actually the numerical approximation already.
Hmm.
But the right way to do it is something like scene or something like that. Actang of the scalar part and the vector part. So, but in implementation, people already try approximation all the time.
Silly question. This box plus is like trying to add to rotation like this.
Yes, you just take it like that. We can leave on with it. Basically, what is a Jacobian? Jacobian is a gradient to update your state. If your state is a rotation matrix, you have to use a box plus, box minus operations. You cannot just use the normal vector box plus minus. What time is it?
when a new scan arrives, we only have pose estimate up to time t. So let's say we are at t. We are going from k, time tk. Now we are going from tk to tk plus 1. So you're saying that we can use the IMU to interpolate between
To propagate.
propagate, yeah,
Mhm.
by interpolation. But
No,
no.
interpolation,
no?
no. That's why you always ask the question about IMU ahead of time, like bias and propagation. So let me explain. This is the formula for propagation.
Propagation is an estimate, it's not an observation, no?
Propagation is propagation. I can't fit it into estimate. I think I can do that.
You have your pose, you get some IMU info, and then you estimate your next pose with IMU data.
Yes.
And between those two, you observe LiDAR points, and then you interpolate.
Yeah, the IMU has more frequency, so it's not, there's not any like interpretation there. It's just use the high frame rate states of the IMU.
I think he was interpolating that.
So if you have IMU sequence like this, right? Like 100 times, like upon cloud, right? Is in this whole continuous stream like this, right? So this, let's just say this point cloud starts at tk, it ends at tk plus 1, right? This IMU point is dj, and this one is dj plus 1, right? And you have a point here, right? What is in between? And it's di, right? So what I do is like I have a pulse, I have a state here. I propagate it to the IMU times, right? Every sample I can update my pulse 1 point, and so for this IMU here, so this for this LiDAR point here, I find this pulse to do the interpolation.
Okay. Yeah. So the question was on this, because if I remember the Loam paper, they said they can work even without this IMU existing by using this plane to plane and point edge feature matching. So because you have points everywhere, let's say you didn't have the IMU, by doing some kind of matching, you could still get this.
Loam, right?
No, the original Loam.
Original loam is along this.
Yeah, because they say we can also work without IMU. IMU only adds to the accuracy.
What I know is, for example, they can estimate the velocity at the time here. Without IMU, you can still estimate the velocity here. And you can still like project your states into this period, into this velocity and your original pose.
Okay. You have to assume this velocity throughout.
Velocity and the rotational rate here. It just to differentiate your previous estimate, you can like extrapolate the states in the next sequences.
By assuming constant
Yes.
velocity in this time frame.
Oh, 30 minutes. So, what are the 4 noble truths? Can someone repeat the 4
You know them, you take the uncertainty, and then your residual, and then Jacobian.
Yeah. I mean, of course, I have to call it the 4-step process. I like the form. It's very simple, right?
You said in your truth, the fourth part, gradient of the cost factor. So the cost factor and residual is one and the same thing.
Yes, the cost factor and residual the same. I mean, yeah, the same. I mean, the language, to be specific, the residual is that difference. The factor is that square. But like,
With the covariance in the middle.
yeah, but we freeball the terms a lot of time. It's interchangeable.
So I also have a stupid question. This is a lifting function. What does it really mean, lifting function?
Tangent space.
Thank you, yes. It's very helpful.
Because like a rotation matrix is, let's just say it's living on a curved space. So when you lift the function means you lift it up means you want to change its parameter on a tangent plane. Let's just say the rotation matrix is on this curved space, and there's a tangent plane. So you can't manipulate things here, but you can manipulate the parameter here. Right? So this rotation matrix here. How do I explain it?
I just read lift. Whatever.
So this is a curved space, right? Does it look like a curved space? So there's a rotation matrix living on this curved space, and you want to influence it with a vector, right? So let's just say you don't know how the formulation is, but what you want to do is you want to influence this with a vector, right? So this is called the lifting function. Is it good enough? I also.
What does exactly influence mean in this context?
Influence means you want to change it to the gradient. I mean, in the most practical sense, you want to update this rotation matrix in the gradient direction. Gradient direction is the direction that is minimizing something, right? So basically, you want to update your rotation matrix. The update action is a vector, and it cannot directly influence the rotation matrix. So we have to lift the rotation matrix up to a tangent space to manipulate it. Yeah, that's why I don't want to bring it up.
So
Tangent space and everything like that. It's just a can of worm.
like one way of the way I think about it is that let's say you want to optimize the rotation matrix, for example, and it's in 3x3.
Yeah.
And then, like Tianmin said, it's on some surface in reality. Like SO3 is some curved manifold. So that is the surface, and your current estimate is here. So now if you would just ignore all this manifold stuff and you just compute the gradient with respect to the rotation matrix, so like the 9 elements, then your gradient might point somewhere here, or like in any direction in this 9-dimensional space. But if you use this tangent space, so you make this reparametrization into like a delta phi, and this delta phi will always be tangent to where you are. So then it can't happen that your gradient points completely away. Like the gradient will always be tangent to where you are currently. So I think that's the...
And then this is like the plane where we are right now?
Yeah,
So
exactly.
the
So
plane
then-
is tangent to the surface.
If you would just blindly add it, like a normal addition, you would still move away from the surface, right? But so I think what you do then is instead you do like the r times x of delta phi, right? And that will all, because that's like a normal, like the x of delta phi, that's a proper rotation matrix. And then if you compose through like a matrix multiplication like that, then you actually, like you compute the gradient on this tangent space, but then you take a proper step on the manifold through the exponential map.
Maybe I shouldn't bring up the lifting here.
No.
Maybe I should just call it the update.
Thank you.
So camera, hey, there's a.
You're the ring, isn't it?
Did you guys watch it all?
Oh, it's the magic on the key or whatever it's called.
But why is it?
What is the new one called?
Ring of power.
Ring of Power.
So it's already taught in while we just like the front end of the camera and everything is taught very nicely here. Right?
It's relocalizing in the,
It's deleting. That's insisting.
No. So I'm not going to teach it again, but like I hate this show so much. But it has a very nice meme. Is it?
I think you muted it.
no.
Yeah.
It's a real quote on the. So what I mean is I'm going to skip the quail egg and I'm giving you my meat. The animation works on the. If you do visual SLAM, you're going to have a feature extraction and association and tracking pipeline front end, right? It's a direct method, so you're based on the features. So we're not going to discuss in detail how we calculate the component and the steep and slope features and track them. But the thing is, after you finish that process, you're going to have a bunch of points in your environment, and each camera can see multiple of them. Can see multiple of these features. So I don't know whether it's generalizable, but in Wind Fusion, the first observation between the feature and the camera, they calculate this space lambda, which is the depth of the image for point. For example, this feature is observed by this camera and this camera. So the depth is defined on this edge, not on this edge. So the if we have a point in the world, right, and the camera is observing it, we don't know its distance from the camera center. So we just assume that we don't know the z, so we just assume that 1 over z being the inverse depth, because they do this inverse because of the numerical stability. And so we start from a point in 3D space. We project it. We divide it, but so we define the inverse depth here, and we define the projection function means we like normalize coordinates with values in the z anymore. So we only focus on the coordinate of the feature. So one camera can see. So this point over here, this camera is going to have x and y coordinate in its projected space. And the same, the point is observed again in the camera. So it's going to have another projected coordinate. So z in the camera A and z is going to be the coordinate of the same feature in two camera. Okay. Any question?
How does it work for the cylindrical?
A limited core camera. I don't know that camera.
Wide angle. It's not.
Wide angle means after that, if you have the camera that has wide angle, they already give the undistortion. So we only deal with the pipeline. We only deal with this number. So whatever camera model, fish eye, and then spherical, something like that. Up at the end of the pipeline, you're going to get this projected coordinates. And you only deal with this one. So this is assignment 2. Simple math. It's just comprehensive, but it's not that like anything alien. So you have a point in the world, right? And so let's just say you have the camera is seeing some point in the world, right? This XY coordinate is going to have some noise, right? And then if you have a depth, right, you can convert it back to the world coordinate, right? But if world coordinate is in the camera frame, right? So like you have a depth, you do the inverse projection, you get the feedback into the world frame, it is in the camera frame. The camera frame is coupled with the IMU. And the IMU is usually in the body frame. I mean, most of the time it's the body frame. So you have to convert from the camera frame to the body frame, right? By this transpose. This is going to be a fixed constant happening in the calculation. Then from the body frame at this time, you go back to the work frame, right? So you project, you transform your point to the work frame, right? And from the work frame, you go to the IMU of the other IMU of the other post. You go to the next pose from the ambient. By this in transform. Then from the ambient you go to the camera, right? And then from the camera you just like do the projection, and you add the noise and you get observation in your camera. So it just has many steps, but it's nothing complicated. I mean, it's nothing like an alien. There's a reason for it.
Can I quickly ask? So the yellow and the red says two different things for B and BF. One of them must be wrong, I think.
Yeah, this one should be CD. One should be CD. I should give you a form so you don't need to do another assignment.
Simple solution.
It's CB. This is the camera thing.
Here, how good is the assumption of eta A and B to the Gaussian, because for that camera, noise model is a bit complicated.
But you can always be more conservative than that model, right? For example, it's going to be not Gaussian, but you can always be conservative and make it into a Gaussian that is more conservative than that noise model.
But if you go like very far away,
This is
the noise-
why I have inverse steps. One because it's much easier to describe uncertainty than inverse steps down to the step.
Mhm.
Because infinity is not as a zero. It's really these incredible large variances.
This is the noise model of an inverse step.
And you normally don't come very close, meaning that 1 over something is not going to be insanely large. And it goes from something not insanely large to 0 instead of something small to infinity, if it's possible to move it.
Covariance, okay, 2D Gaussian, so you just put a weighted here. The residual is, what is the residual again? What is this step? What is the thing to do in this step? Throw away the noise, plug in the estimate, right? Throw away the noise, plug in the estimate. Subtract the observation from the map. Subtract your model from the observation. In Rinse Fusion, these extrinsic are made into state estimates. So they also estimate the camera to IMU transform in real time, which I don't know. I have an opinion, but it's not. So assignment is basically just go look into that code and write down what they did, and doable it. It's already there. It's just in CVP. You just need to write it in nice latex Localization, and you can also discuss. We're also going to have peer review, right? So your reviewer will point out the error for you. Okay.
Do I have a peer review if no one knows how to solve it?
Then you send an email.
Not how I did it.
Then you email Kim Hong Pro, my Chinese Pro. Can you send me your technical report or something on this proposal?
Like appendix, could you send the appendix, please?
Yeah. So you can do it. I trust you. I have big faith in you.
Okay.
I think we should keep it to the next one because this one is going to be very hardcore.
This one would be okay.
No, the
Yeah.
Perfect for a Friday afternoon.
Yeah.
Just give it to the next one. I think give yourself a week or so to digest the linear algebra and all of the.
Yeah.
But just stick with the four noble truths. Start from that.
Don't you just integrate a little bit?
I think this whole ideal thing is simple if you just integrate it. The complexity comes from the noise. The step number 2. It's the
Then step 3, you ignore the noise.
yeah. Step 3 you throw away all the noise and you just. But I think we can keep it for the next session.
But so the noise is propagated with a Jacobian vector.
Yes. Then you have to use the right Jacobian formula before that to keep it propagate back, and then you have to do like first order approximation all along the way. This literally this one.
If you would like to.
You have to keep approximating.
My hands are already dry because it's cold.
So any other question?
I had a question. I didn't quite understand the covariance part in the beginning when I think you asked like why doesn't the covariance depend on the distance?
You mean
for
that
UVB, I think.
because in ultra wideband, for the ultra wideband that I worked on for level, we just have one beacon A, so-called the transmitter, and this one is the receiver. This one just send out the signal, this one replies, and then you just do the time of flight, and then you get the distance. So the error is in the time measurement. The error is in the time. So if you have the true time, you just plus some time error. So it's a additive noise. It's not time distance dependent.
Ideally.
Yeah, ideally.
But you do get like wall reflections and stuff like
That multipath effect is usually handled by the waveform analysis inside the sensor directly. So if they look into the waveform and they say, okay, there's like multiple peaks like this, they're going to say, okay, this is our they throw away. They don't send me any distance at all. Is it okay?
It's
Time
just
of
hard.
flight?
Well, what distance equal to time?
Time of flight?
Delta t times c, right? You take delta t divided by the.
Yeah, see, that's
Light, the speed of light,
Well, in
Oh,
time, not
speed.
like-
and then when you measure the time with some like errors, you just have an
c
additive
times
noise.
delta t.
Yeah, it should be C time.
Am I maybe
Wait,
I completely
wait.
misunderstand, but that's delta t times c.
Yeah.
Yeah, yeah.
Yeah, it should be.
Yeah, gel me for it.
Oh, it's
Could be in
confusing
jail.
life.
I was getting worried myself. I'm completely stupid.
Me too.
Yeah. Is it like in
Maybe it's
GPS when there's in GPS when you don't know the clock, there's in GPS you don't have these two-way time of flight. You just have one way time of flight, and then you have to synchronize the clock somehow. So the distance couples with that uncertainty in the clock phase. So it can become a distance dependent noise.
For me, it's also you can think about it as so for the side scan sonar, it's the time, it's the distance, it's the sound traveling distance hit.
Yeah,
So
it's
it's the
the
same.
principle is
Yeah.
almost the same. It's just that yeah. I actually did the analysis. I just like I put the receiver away from me for 10 meters, and then I collected 100 samples, and then 20 meters, 100%.
But for a Lidar, for example, don't you normally say that the noise is dependent on the range of the hit?
Yes, there is that effect where you have the beam divergence, and then you can have that kind of error. Patrick knows it. But I'm born like 20 years later, so I have better LiDAR, so I don't really suffer from it.
Yeah.
But so you're saying for a Lidar, even if you hit 40 meters away, you get the same error as a meter away.
I would also say that the number you put in there is not just the error in the like low level distance. It's incorporating a lot of other things, and those other things are usually larger than that specific distance measurement. It also has to factor in the fact that the wall isn't completely flat. Maybe you're approximating the brick wall there as a planar surface, and well, the brick, there are cracks in it and all sorts of things that are centimeter level maybe. So
I still find it's hard to buy, I don't know why.
but if you were using stereo vision instead, or RGBD, then it would definitely not be. I mean, I think if you read the spec, it will say that it's distance dependent.
Mm.
It's just that in here, it's too detailed to bother, I would say. If it's RGBD camera, then it's very large and you need to think about it.
Yeah. I mean, with the RGBD camera, it's very obvious.
Yeah.
But it's very non-linear also.
Yeah.
It's like more like the texture of the wall matters more than the distance. Right programming.
Where is the noise? The velocity, points.
This is a residual block.
Yeah. You see this square info?
Yeah.
This square info is the so our cost function is like R sigma R, right? Our cost function is R sigma R. And R here is like H minus Z. Yeah. So they are doing the residual here. But see, this matrix is the noise, so they create the sigma. So they make it into this form. Right? So they calculate each of the block, the residual block by this square root info. The inverse of the Jacobian, sorry, the inverse of the covariance matrix is the information matrix. So they calculate the square of that matrix and they lump it into this form. So what they need to do, what I want to show is we want to find the noise. How we calculate that square root info. It's a constant. It's a freaking constant, isn't it?
No, it's just declared as a static.
But if it's like this, it's not going to be changed.
See?
Unless you change.
Find where it's
Because this one is declared here, right? It's going to be external somewhere.
Yeah.
So it's going to be a constant in the whole program, right? Let's try to find.
Such web.
So it's very easy. I mean, every time I talk about estimation problem, people will talk about this noise determining something.
You can probably search for SQRT for
Yeah,
that's
it's,
happened every time.
Initial bias.
Oh, it's just 1,000. That is fine.
So you see, they also just set a constant here, right?
Ah, but there the initial bias factor H. But again, it's.
So in their file here, they just like initialize it once.
I love that they have 1 over 0.001. Which is just like it does.
Make it clear.
So what I mean is, yeah, it's very common for people to argue. Okay, why don't we do this noise in a more dynamical, like with a higher complex model? But when the engineers get to put their hand onto the problem, they just like freeball the numbers, and it works. If it doesn't work, then they think about it.
But this is basically how much you correct with this information.
Yeah, I think that's why the other day when we show the cost function running, it's like hundreds.
Yeah.
Doesn't actually, I don't know,
I mean, I
because
think
the numbers are all like
arbitrary.
random, arbitrary.
But there is
For
like,
some cases, you can easily guess that. So,
Yeah.
for example, the visual slant things, you do a reprojection error, and the pixels. So you got the pixels reprojection. Maybe like you have a distribution that indicated it was
Yeah.
like 10 pixels within 10 pixels, and you just put 10
Yeah,
pixels
yeah.
there.
I think somewhere they do a 1 over the focal length in this in this code. somewhere they calculate the noise, this square involved by having 1 over focal length in that. So it's related to the pixel and the intrinsics of the camera. But they also guess everything. So you say it's based on the pixel, they also guess the pixel. Right? It's based on the focal length, they also guess the focal length. I think they hard coded their noises in this software. They hard coded all the noise. I don't know in the OBLAM whether they hard coded the noise. Do
But
they?
I guess focal length you calibrate, right? Or
Yeah. It's based on
No, I don't.
vibration.
Yeah. For the camera intrinsics, usually when we get on the caliper, it's just the tangential and distortion. So like 4 numbers.
You could estimate for that.
Yeah, that's right. But that's why I say Lidar is actually the most convenient one. Agree now?
Yeah, agreed.
Yeah.
Yeah, I use the
just
Lidar
plug it in,
all the
get the
time. I
number.
didn't have camera.
Plug it in, get
Objection.
Yeah.
the point in 3D space. And then
Yeah, I
do,
agree with you.
It's
But
too
then-
expensive.
No,
it's like
it's not.
$2,000 one
Yeah.
good Lidar now.
And in China, it's even cheap. Yeah,
Okay.
I can sure that we can get maybe really cheap, 10 times cheap than you.
Come on, I have a colleague.
Yeah.
But the price is like it's based on the precision of the LiDAR scans.
How much was the one we had in the robot box?
$200 maybe.
It's decent.
When you get your hand on the camera, then you have to worry about its projection model, whether it's pinhole or whether it's fish eye, something like that. And then you do calibration, and then you happen to shake it so much in this direction, but not in this direction. So your estimation, your calibration fails to converge, something like that.
Okay, I mean motion blur because of that.
No, the intrinsic calibration. You do the calibration, you have to shake it
Yeah,
around,
yeah,
right? And then
yeah.
sometimes I put it into an 8 kg disc, and then shaking it around is a pain. So then you get a LiDAR, you just like hook it up and then get the numbers out.
But if you have multiple LiDAR, you have to do that also, right? If you have multiple LiDAR, if you are rich, like for LiDAR, we did like OBLAM, yeah. The
OBLAM, did you?
Yeah, or not I did, but my group mates did.
They also, at the end of the
We
day,
have 4 LiDARs, each one have 16 4 channels, and we have to do also calibrations like extrinsic
But
calibration.
you can actually spawn them into a
Yeah.
corner
Yeah, that's much easier.
and then do the ICP. It
Yeah.
works more easily, no need to move anything.
You're right.
So agree with me, the camera is. I mean, if I have money, I'm not going to buy a LiDAR. If I have money, I'm going to do research on a LiDAR.
but that's only taking SLAM into account, I guess. If you
No,
do like
like-
perception, I think I'm not so.
I think
It's not that
Where's your
obvious.
image? Where's the intensity image?
No, but I think also just from the data sets that you have, so much harder to annotate LiDAR versus images.
Yeah, you're right also about this. But in